Welcome to our fourth video. We are looking at angles between two lines, angles between a line and a plane, and angles between two planes. Okay, first of all, angles between two lines. Well, if we're given the equations of two lines, then we're given both the direction vectors. Let's call them u and v. In the textbook they give you this formula, which is derived from the scalar product, and it always gives the acute angle. Why? Well, if we were to move the direction vector u here and the direction vector v here into their usual configuration, we would have an obtuse angle here. Then we'd use the scalar product as usual. Cosine of theta would have to be a negative value because cosine of an obtuse angle gives a negative value, which is okay. We would work out theta with arc cos as follows, and it would give us the obtuse angle. Nothing wrong with that, but this formula here always gives the acute angle, and here's the reason. I'm sure you remember the graph of arc cos. It looks like this. However, when we do, as the textbook said, arc cos of the absolute value, then that has a transformation which we studied in chapter 2. Any function where you compose the function with the absolute value function takes this part and reflects it in the y-axis to give this part. Therefore, the range of arc cos absolute value of x is 0 to pi over 2, or 90 degrees. That's why it guarantees the acute angle. So if we look at an example, find the angle between these lines. They're given in Cartesian form, so we can do a little bit of revision. This is the Cartesian form. All of these were equal to lambda, and when we rearrange that, we get x in terms of the fixed point and lambda times L. And when we rearrange that into the vector form, we get this, which is what this form is here. This is the fixed point on the line, and this is the direction vector. So with example 40, the first job is to write the equation of the line in this form, because then you can just read off LMN as the direction vector. Maybe you should pause for a second to try and write that down. Oh, there's the first one. Okay, pause for another second to do this one in Cartesian form. There it is. And then we can read off the two direction vectors. And then I'm going to leave you to just find the angle between them with the formula. And check your answer in the textbook. It's example 40. Okay. Now, the angle between a line and a plane, I always imagine the red line here as you holding a pencil at an angle to your desk, and the light above you from the ceiling shines down and leaves a shadow underneath it, which in physics we call that a projection, the projection of the line onto the plane. So the angle between a line and a plane is defined as theta, which is the angle between the line and this projection. And here's the formula here. You notice it's got arc sine. It's the same as the one we had before, but it has arc sine. So the question is, why is it arc sine and not arc cosine? And it's an easy answer. If we look at this formula here, which is what we did to find the angle between two lines, this finds the angle between the direction of the line and the normal vector of the plane, which is alpha. But that's not the angle we want. We want theta. But it's obvious that theta is 90 minus alpha. So hence, theta is 90 minus this thing, which is alpha. So I ran out of space. Instead of writing this, I just wrote a blob. Theta is 90 minus arc cos blob. Actually, I think I missed the C out of arc cos. Therefore, arc cos blob is 90 minus theta. Said differently, blob is cosine 90 minus theta, but we all know cosine 90 minus theta is sine theta. Therefore, theta is arc sine blob. What is blob? It's that thing. So that's where that formula comes from. Okay. So here's an example. Find the angle between the line and the plane. So this line is not really given in vector form very conveniently. To make it into vector form like this, you have to remember that I is the unit vector 1, 0, 0, j 1, 0, 1, k 0, 0, 1, etc. And then just rearrange it so we have a fixed point and lambda times the direction. And also with this plane, it's easy to write down the normal vector, as we saw in the previous video. I'll give you a second to do that. There it is. So then, to find the angle between the line and the plane, you have to use the formula from 2 pages ago with the arc sine on these. Remember, the normal vector is always the coefficients of x, y, and z in Cartesian form. And again, check your answer from the book, example 42. Okay, next video is angle between two planes.